Namaskar viewers. In our previous session, we discussed about the acidic strength of carboxylic acid, sulfonic acid, a comparative study of the acidic strength of carboxylic acid, sulfonic acids and aromatic carboxylic acid. We also discussed the different factors which influence the acidic character of these acids. Now, in the next session, this session will be around the acidic strength of isomeric substituted benzoic acids. So, we will continue with our discussion, and as you can see in this slide, we have the acidic strength in isomeric substituted benzoic acid, where a substituent is present at ortho, meta and para position, and how it affects the acidic strength. The factors which affect the acidic strength in ortho, meta and para substituted benzoic acids are resonance effect and the inductive effect. So, these two factors will govern the acidic strength. First, the resonance effect which is there will govern, because resonance effect is experienced maximum at ortho and para positions as compared to meta position. So, if you have a negative resonance effect, then this minus R effect will be observed maximum at ortho and para as compared to meta. The second effect is inductive effect. Inductive effect will be distance dependent. That means when a substituent is nearer to the functional group, its inductive effect will be observed maximum. So, whether it is an electron releasing or an electron withdrawing effect, it will be observed maximum at ortho position, then followed by meta, and at para position the inductive effect will be experienced least. However, when we talk of resonance effect, it will be observed maximum at ortho and para and lesser at meta position. Now, let us take the example of substituted benzoic acid. Here we are talking of 2 nitrobenzoic acid, 3 nitrobenzoic acid and 4 nitrobenzoic acid. That means the nitro group in benzoic acid, it is substituted at ortho, meta and para positions. Now, the substituent which is there is nitro group, and this nitro group has a minus R effect and a minus I effect. So, both these factors, that means minus R and minus I, basically both are withdrawing electrons from the ring system. So, minus R effect will govern that ortho and para isomers will be more acidic than meta. Now, minus R effect has governed the acidic character of ortho para more than meta. Now, I have to see that out of ortho and para, which one will be more acidic. Now, for this purpose, the inductive effect, the minus I effect will come into picture. Now, inductive effect, as it is distance dependent, so electron withdrawing effect of or the minus I effect will be observed maximum at ortho and lesser at para. So, out of ortho and para, ortho will be more acidic, then para and then meta. So, that is the order of acidic strength in ortho, meta and para nitrobenzoic acids. The next is the case of 2-hydroxybenzoic acid or ortho-hydroxybenzoic acid, meta-hydroxybenzoic acid and para-hydroxybenzoic acid. Here the substituent is OH group. Now, this OH group has a plus R effect and a minus I effect. Now, we discussed earlier that it is the resonance and the inductive effects which will be the governing factor. As we have discussed earlier, that electron withdrawing groups, they increase the acidic strength, and electron releasing groups, they decrease the acidic strength. So, when the OH group is having a plus R effect, due to plus R effect, it is going to release electrons towards the benzene ring, and therefore it will decrease the acidic strength. So, here plus R effect is not of importance to us. So, the governing factor here will be the minus I effect or the minus inductive effect, through which electrons will be withdrawn from the ring and therefore they will stabilize the carboxylate ion. So, here since the inductive effect is the governing factor and inductive effect is observed maximum at ortho followed by meta and para. So, the order of acidic strength in these cases will be that ortho will be more acidic than meta and meta will be more acidic than para. Now, if you look at the pKa values of these three isomers, you will find that the difference in the meta and para is there, but the ortho isomer is highly acidic in nature as compared to meta and para. Although in all the cases I have the same substituent which is there, so why at ortho position there is such a tremendous increase in the acidic strength? Now, this can be explained here that orthohydroxybenzoic acid will result in the formation of orthohydroxybenzoate ion. As you all know, orthohydroxybenzoic acid is also known as salicylic acid. So, salicylic acid will result in the formation of a salicylate ion. Now, the acidic strength of any carboxylic acid is dependent on the stability of carboxylate ion. In case of salicylate ion, there is an intramolecular hydrogen bonding. That means the carboxylate ion and the OH group which is present at the ortho position, so they will undergo hydrogen bonding, and since the hydrogen bonding is taking place within the molecule, so it is an intramolecular hydrogen bonding. The intramolecular hydrogen bonding will increase the stability of salicylate ion because forces of attraction lead to the stability. So, stability due to intramolecular hydrogen bonding will make this salicylate ion highly stable, and more the stability of carboxylate ion, higher is the acidic strength of the corresponding acid. Since salicylate ion is highly stabilized through hydrogen bonding, so salicylic acid will be a strong acid, as you can see here, right. So, here we have seen that how hydrogen bonding affects the acidic character. So, hydrogen bonding has contributed towards the stability of the carboxylate ion and hence an increase in the acidic strength. Let us take another example where we have orthochlorobenzoic acid, metachlorobenzoic acid and parachlorobenzoic acid. Now, chlorine which is there has a plus R effect and a minus I effect, and out of these two, plus R is electron releasing, so that is not going to increase the acidic strength, it will basically destabilize the carboxylate ion. So, the governing factor in this case is minus I effect of the chlorine. Now, minus inductive effect is observed maximum at ortho followed by meta and para. So, the order of acidic strength in these cases will be ortho will be more acidic than meta and meta will be more acidic than parachlorobenzoic acid. Now, in the another example of the carboxylic acid, here we will be discussing how the steric hindrance affects the acidic strength. Now, this is the case of cis-cinnamic acid and trans-cinnamic acid, and cis-cinnamic acid is found to be more acidic than trans. Now, in case of cis isomer, the benzene ring and the carboxylic group which are there, they are present on the same side of the ring, right. Now, when they are present on the same side of the ring, there will be a steric crowding or a steric hindrance, due to which the molecule, the planarity will not be there. So, to attain stability, the molecule will be a bit away from the planarity. However, in case of trans-cinnamic acid, the phenyl ring and the carboxylic group, they are present on opposite sides. So, there will be no steric crowding. The steric crowding is not there, so the double bond which is there and they will be in the same plane. As a result, delocalization will take place. As you can see in case of trans, the electrons from the pi electrons from the double bond will be shifted here and the electrons will be shifted towards the carboxylate ion. So, due to increase in the negative charge on carboxylate ion, the carboxylate ion of trans-cinnamic acid will be less stable. However, this delocalization is not possible. That means the electrons will not be given to our carboxylate ion in case of cis-cinnamic acid. So, cis-cinnamic ion will be more stable as compared to trans, because in trans there will be an increase in the negative charge on carboxylate ion. So, the stability will be less. So, since in case of cis the carboxylate ion is more stable, so cis isomer will be more acidic than trans. So, here we have seen how steric hindrance or the steric crowding affects the acidic strength. Now, let us move to the other functional groups, which are alcohols. Now, the acidic strength of alcohols, just like we have discussed in case of carboxylic acid, will be dependent on the stability of the alkoxide ion, which is formed by loss of proton of alcohol. So, if we compare the acidic strength of primary, secondary and tertiary alcohol, so they will form the corresponding primary, secondary and tertiary alkoxide ions. Now, in case of primary, we have only one alkyl group which is having a plus I effect. So, it is going to give electrons towards this oxygen and it will increase the negative charge on this oxygen. When we have a secondary alcohol, there the alkoxide ion is having two such electron releasing groups, alkyl groups attached to carbon. So, they will increase the negative charge on oxygen to a greater extent. In case of tertiary, there are three such alkyl groups. So, the negative charge density on oxygen will be maximum. So, in case of tertiary alkoxide ion, the intensification of negative charge takes place because of three alkyl groups and therefore, it will be least stable. And primary relatively will be most stable. That means primary alcohol will be more acidic than secondary and secondary will be more acidic than tertiary. Now, the another aspect of the acidic strength is the size. Size also affects the acidic character of organic molecules. For example, when we compare the acidic strength of methane thiol and methanol, in both the cases we will have formation of the conjugate bases, that is methoxide ion and methane thiolate ion. It is the stability of these ions which determines the acidic strength. In case of methane thiolate ion, sulfur is there and sulfur has a higher size or a larger size compared to oxygen. So, the negative charge is delocalized over a larger surface area and therefore, its stability will be more. In case of oxygen, the same negative charge is delocalized over a smaller surface area because size of oxygen is less than sulfur. So, it means methane thiolate ion will be more stabilized because of a bigger size of sulfur and therefore, methane thiol will be more acidic than methanol. Next, the acidic nature of phenols. Now, in case of phenol, OH group is directly attached to your benzene ring and the acidic character is attributed to the plus R effect of OH group. That is, the OH group is going to give electrons towards the benzene ring system. So, it will participate, the lone pair on oxygen participates in delocalization with the benzene ring system. And this will result in the formation of contributing structures where you can see that the oxygen hydrogen bond will become weak bond because oxygen is carrying a positive charge. So, hydrogen can be easily given out and therefore, phenols will exhibit an acidic character. Now, when phenol loses a proton, it will result in the formation of phenoxide ion and this phenoxide ion is further stabilized through resonance. Now, since resonance is there, therefore, we can say that your phenoxide, the phenols will be more acidic than alcohols because in case of phenols, the phenoxide ion is stabilized through resonance. The effect of substituent on acidic strength. Now, if I have a paramethylphenol and parachlorophenol and paranitrophenol, what will be their relative acidic strength? As we have discussed earlier, methyl group due to plus I effect will increase the negative charge on phenoxide ion. It will destabilize the phenoxide ion and therefore, will decrease the acidic strength. Chlorine, which is there on the other hand, due to minus I effect will stabilize the phenoxide ion and therefore increase the acidic strength. In case of nitro group, there will be a minus I effect and a minus R effect. So, both inductive and resonance are there in the picture, and both of them are withdrawing electrons and they are stabilizing phenoxide ion to a higher extent. So, nitrophenol will be most acidic of these three. Again, when we talk of the substituted phenols, that means where we have ortho, meta and para substituted phenols, it will be the resonance and the inductive effect which will govern the acidic character. And in case of orthonitrophenol, the nitro group which is there is having a minus R effect and as well as a minus I effect. So, due to minus R effect, ortho and para will be more acidic than meta. So, one thing is clear that meta will be least acidic. Now, out of ortho and para, which one will be more acidic? That will be governed by minus I effect. And as per inductive effect, ortho should be more acidic than para. But in this case, we have observed that para is more acidic than ortho, and the less acidic character of ortho is attributed to the hydrogen bonding. Again, in this case, what is happening that orthonitrophenol itself undergoes intramolecular hydrogen bonding. Due to intramolecular hydrogen bonding, hydrogen cannot be given out easily and therefore it becomes less acidic, because acid is nothing but the one which can easily lose a proton. Here, loss of proton is being restricted due to hydrogen bonding. So, orthonitrophenol is less acidic as compared to para. Now, let us come to the basicity, the functional groups which show basicity. Now, basicity is nothing but the ease of availability of electrons which can be shared with other electron deficient species. For example, when we take amines, in case of amines, when they react with water, so amines, because of lone pair of electron on nitrogen, these electrons can be given to an electron deficient species. It can capture a proton from here and will result in the formation of ammonium ion, which is a conjugate acid. So, amines, they show basic character or they show basicity because of the presence of this lone pair of electron on nitrogen, and this lone pair can be easily given to the other species. So, the ease with which the electrons which are present can be given to other species determines the basicity of a molecule. Now, as you can see in this slide that we have amines, the NH2 group is attached to different type of alkyl groups. This is ethyl group, this is isopropyl, and this is a tertiary butyl group. Now, the plus I effect, alkyl groups, they release electrons. So, plus I effect of tertiary butyl is more than isopropyl, which in turn is more than ethyl. So, increasing plus I effect will increase the electron density on nitrogen, and therefore, the basicity will also increase with an increase in the plus I effect of alkyl groups. Next, let us compare the basicity in primary, secondary and tertiary amines. Now, in primary amines, we have an alkyl group which is attached to nitrogen. The alkyl group has a plus I effect. In secondary, two alkyl groups are attached, so there will be an increased plus inductive effect, electrons will be released more. And in case of tertiary amine, three alkyl groups are attached to nitrogen, so electron density on nitrogen will be further increased in presence of three alkyl groups exhibiting a plus I effect. Now, as per this, the order of basicity should be that tertiary should be more basic than secondary. But it has been found that in aqueous phase, the basicity order of amines is that secondary is more basic than primary, which in turn is more basic than tertiary. So, in aqueous phase, mind it, whenever we talk of acid-base reactions, we are talking these acid-base reactions in solution phase. So, in aqueous phase, the basicity order is observed this. Now, let us see why it is so. Secondary is more basic than tertiary, and there are two factors which are affecting the basicity. One is the steric hindrance and the other is the solvation effect. We are comparing the secondary and tertiary in this case. Now see, this is a picture of a tertiary amine, as you can see here. This is the nitrogen, where you can see lone pair of electron present here, and this nitrogen is surrounded by 3 methyl groups. As you can see here that there is a steric crowding in tertiary amine. So, although the electrons are available on nitrogen, but then nitrogen cannot give these electrons readily to any other species because the path of giving that is been blocked by these bulkier alkyl groups. So, electrons are there, but they are not available for donation to other species. So, the basicity of tertiary amine will decrease. So, because of steric factors, tertiary will be less basic than secondary. The second effect is the solvation effect. We have a secondary amine which will take up a proton, will form a conjugate acid which is dimethyl ammonium ion. Similarly, tertiary amine will take up a proton and will form a trimethyl ammonium ion. Now, it is the stability of this conjugate acid which will determine the basicity of amine. The dimethyl ammonium ion, as we can see here, is stabilized because the solvent molecule, we are talking of aqueous phase, so the water molecules will form bonding with the hydrogens which are present on nitrogen. 2 hydrogens are present, so solvation will be more in this case. In case of tertiary amine, there is only 1 hydrogen. That means solvation in case of tertiary amine will be less. More the solvation, more are the forces of attraction, more is the stability of this conjugate acid. So, this ammonium ion will be more stabilized in case of secondary amine as compared to tertiary. As a result, secondary amine will be more basic than tertiary. So, basicity of secondary amine is more than tertiary amine because of higher solvation in case of secondary amine. Now, let us compare the basicity of amine and amides. Amine, as we can see that amines are more basic as compared to amide. In case of amine, we have a plus inductive effect of alkyl groups. Now, why is it so? Let us see here, we have this is an amide. In case of amide, nitrogen is there, lone pair of electrons are present on nitrogen, but these electrons are participating in conjugation with the carbonyl group because lone pair is in conjugation with a pi bond of carbonyl group. So, resonance will take place, and due to resonance the electrons are delocalized over this carbonyl group. This delocalization will make the availability of electron less. So, if these electrons are not readily available for donation to other species, the basicity will be less. As a result, the amides which are there, they are less basic as compared to amine, because in case of amines the lone pair of electron on nitrogen is there, and further it is attached to an alkyl group, and the plus I effect of alkyl group is further increasing the availability of electron on nitrogen. As a result, basicity of the amine will be more. Aliphatic amines will be more compared to corresponding amides, where the availability of electrons has been reduced due to this resonance effect, due to this delocalization. Now, let us compare the basicity of aliphatic and aromatic amines. Both are amines. What is the difference in the two? Now, in case of aliphatic amines, the carbon to which NH2 group is attached is sp3 hybridized, whereas in case of aromatic amines, NH2 group is directly attached to benzene ring and the carbon of benzene rings are sp2 hybridized. sp2 hybridized carbon is more electronegative than sp3 hybridized carbon. That means your aromatic amines, when we talk of, so the carbon which is there being sp2 hybridized, being more electronegative, will take away electrons from benzene, and the availability, it will take away electrons from the nitrogen, and therefore availability of electrons on this nitrogen will be less, and so will be the basicity. So aromatic amines are less basic than aliphatic amines due to high electronegativity of sp2 hybrid orbitals. Secondly, in case of aromatic amines, there is plus R effect which occurs, and due to this plus R effect, the electrons which are present on nitrogen are participating in delocalization with the pi electrons of the benzene ring system. And due to this plus R effect in aromatic amines, the basicity decreases because there is a decrease, there is a reduction in the availability of electrons on nitrogen. The effect of substituents on basicity, as we can see here, that the nitro group, being electron withdrawing in nature, will take away electrons, will decrease the availability of electrons on nitrogen and will make it less basic, whereas electron releasing group like methoxy will increase the electron density on nitrogen and will make it more basic. And finally, when we compare the basicity of pyridine and aliphatic amines, again in case of pyridine, the nitrogen carrying the lone pair of electron is sp2 hybridized, whereas in aliphatic amines, nitrogen carrying the lone pair of electrons is sp3 hybridized. sp2 being more electronegative will make it less basic as compared to aliphatic amines. So here we have seen the different factors which are affecting the acidic and basic behavior of organic molecules, and we have seen that the acidic character will be increased in presence of electron withdrawing groups and it will decrease in presence of electron releasing group, whereas in case of the molecules which show basicity, the electron releasing groups will increase the basicity and electron withdrawing groups will decrease the basicity of the organic molecules. Now, these are the references which we have taken from this, the Mehta and Mehta Organic Chemistry which is there. We have the book by Claydon, Laurie Richardson, Wade, and they will help you in understanding the concepts which we have studied so far. I hope this lecture has been helpful to all of you in understanding the fundamentals of the acid and base concept in organic chemistry, which will further help you to understand the relative acidic and basic strength of organic molecules and will be helpful in determining the chemical reaction transformations and in understanding the mechanism of the reactions. Thank you so much for listening and a happy learning to all of you. Thank you.